We are going to study interrupt in this lecture. Every microcontroller has a set of interrupts, sources of interrupts, like the interrupt coming from the input port, and there are so many input ports. So there can be a large number of sources of interrupts. Then there is an interrupt due to timers, an interrupt from the AD converter, an interrupt from the clock, and an interrupt from serial data coming in. Likewise, there can be a variety of sources of interrupt. And out of that, we are going to use interrupt due to input ports where we have connected 7 different keys, and interrupt due to serial communication because the MP3 module keeps talking to the microcontroller on serial port that we have seen before. So let us have a look. You can see here, as I have mentioned earlier also, 1, 2, 3, 4, 5, 6, 7. There are 7 keys which are connected here, and they have the potential to cause interrupt. Whenever the key is pressed or released, it may cause an interrupt. That is one. And second is, if you look at this device, which is the MP3 module, it sends data on serial port to our microcontroller. So microcontroller need not keep looking at this pin. It will keep doing its own business, and this information, when it comes from this pin 3 to this pin 3, it is a serial business. There is a string of serial bits which comes and eventually causes an interrupt, and then our CPU will respond to that interrupt. So these are the two main interrupts we are going to see. If you wish to understand interrupts and a variety of sources of interrupts, you can have a look at this. You go to page 70 of the user manual, and here you will get all the information. In fact, it starts early. You can see it goes to page 58 perhaps. It describes all the interrupts. There's the interrupt controller. Is at page 59. You will see a description of interrupts started here. So there is a variety of interrupts. You can study it for your interest, but my idea is to use those things that we need and gradually develop our knowledge, so the knowledge appears realistic for you. What we have done in our program to handle these interrupts, let us see. I have briefly discussed about the interrupts caused by the input port, the PD3 interrupt. So there is a register PD underscore CR2, and if we set the bit, this is bit 0, this is bit 1, this is bit 3, this D0, PD0, PD1, PD2. So this bit has to be 1, and so this is PD0, PD1, PD2, PD3. If I set this bit 1, then a change of level at PD3 will cause interrupt. That is one thing. We have already made this port D3 as input, so that is not an issue. And in addition to that, we have to tell the system what kind of change at PD3 should cause interrupt. We have to be very clear about that. So we have a register. You can see that register at page 70 of our manual. Let us go to page 70 of the manual. Page 70 of our manual, 70. enter. So this is the register, external interrupt control register. In this register you can see that this is for port D, this is for port C, port B and port A. These are the interrupts we can go for. Right now I'm discussing only the PD, that is port D. If I set, there are two bits, bit 6 and bit 7 of EXTI CR1. EXT means external interrupt and this is control register 1. If I look at the bit 6 and 7, they are dedicated to port D. What these two bits do? If the two bits are 0, 0, then anything that drives port D from 1 to 0 and stay at 0, then an interrupt will be caused. It is not just an edge. From 1 to 0 it falls as an edge. It will detect that edge and then it will see the logic level staying 0 and then it will generate an interrupt. If it is 0, 1, then it will look at the rising edge only. If it is 1, 0, falling edge. If it is 1, 1, then it is a rising and falling edge, both. So it should rise and then it should fall and then only it will cause interrupt. Here, it will just fall, that is enough, and then it will cause interrupt. In this case, it will just rise. If you recall, in our case, when I press the key, the potential or the voltage at PD3 goes to 0. So from logic 1, it goes to 0, it means it is a falling edge, and we want the interrupt to be caused when the level becomes low. So this low level is important for us. Therefore, what we have done, in the register EXTI CR1, we have set these two bits, bit 7 and bit 6 as 0, and we have not disturbed any other bit. This is what we have done. Let us see. If you look at this, PD3 CR1 external I CR1, this is where we wanted to go. So external I underscore CR1, we have ended it with 3F. 3F means what? 3F means 0, 0, 1, 1, 1, 1, 1, 1. So we have ended this register with this data. As if you recall, if we end with 1, there is no effect. The register will continue to be what it was. The content will not change. But if I end with 0, then that position in the register becomes 0. So the first two bits, bit 6 and bit 7, have been made 0 in this process. So the second thing is this bit PDCR2, this bit has to be made 1 to ensure that it can cause interrupt. So whether it will cause interrupt or not will depend upon whether this bit is made 1 or not in the register PDCR2. And what kind of change will cause interrupt is decided by this kind of registers. And therefore these two we have to take into account in order to ensure that the interrupt comes in the correct way. So we will see what happens. When we started building our program, our project, we saw that the compiler has by itself created a main file which we have substantially modified and another file which is interrupt vector.c, stm8 interrupt vector.c. This is that file. If you see what is written here, basic interrupt vector table for STM8S devices. So it is not restricted only to our STM8S003 device. It can handle all devices of the STM8S series, and therefore the content of this file is highly generalized, as you can see. So If it is 903, it can be 208, it can be 207, 105, 103, and so on. So all possibilities have been taken into account so that you are not stuck only to STM8S003. And when you go through this file, you will also see the large variety of interrupts that it can handle. In fact, you'll see the sources of interrupts. There is an interrupt when you reset, it causes an interrupt. And it takes the program control to a specific location. When you cause an interrupt here called trap, then it takes the program control to another location. Then external top level interrupt, it is called TLI, or auto wake up from halt, that is an interrupt, or clock controller also can generate interrupt. And this is where we have come. The port D causes interrupt. This is interrupt request number 6. External interrupt, port D. We are going to use this interrupt. And so when I say that it takes program control to a specific location, so for every kind of interrupt we have a specific location, and we use the word vector to mean that location, and therefore we use the term vector, interrupt vector. And this is a definition of the interrupt vectors. So this is the way we have to define the interrupts. For certain interrupts may not be available for some microcontrollers. Like 003 does not have CAN interrupt. CAN means control area network. So 003 does not handle CAN. So this CAN interrupt is not available for 003, but it is available for STM8S208 because that handles CAN. Likewise, something for 903. So all you have to remember is this table tells us, in fact tells the compiler, that these are the possible interrupts. So it is basic interrupt vector table, and how to make use of this. This information is to be used by us in this file. This file I have termed stm8s it for the tutorial. And if you see, this is main interrupt service routines. All those service routines are here, and where these will go will be decided by this. When an interrupt comes, where it will actually vector means where it will be driven to, that address, that is called a vector. So this will tell you what to do when the interrupt occurs, and this tells you where the program has to be written to handle that interrupt, right? So we will not change this. We will not change stm8s interrupt vector.c. It has been created by the compiler itself right at the beginning. What we will do is we will play with this. To handle the interrupts, we need to write programs, and we will write those programs in this file, which is this file. And the name of the file is stm. If you go to the top line of the page, that is stm8s it. Good. So when the interrupt at PD occurs, then what it will do? So whatever it has to do will have to be written in this area. Interrupt handler, external interrupt, port D, IRQ46. This is interrupt number 6. And what you will do, between these two braces, whatever you write, that will be executed. This may be a simple instruction. Here I have given a very simple instruction. B is equal to 0x10. What 0x10? Just something. Just to show that some initialization happens. In terms of decimal, 10 stands for 16. So you'll see that B will either be shown as having 10 or 16. So this is one thing. And for the USART, that is for serial communication, this is what we do. Okay, we'll come to this later. Right now we are talking only about the port D interrupt. So we will come here, and these breakpoints are given to help you see what happens. Normally there will not be any breakpoints and system will be running continuously. It will not break anywhere. So we can see such a large number of sources of interrupt. I have given, I check the port D and check if bit 3, let me show it in a 0, it means 0 0 0 0 1 0 0 0. So we are trying to check this bit 0 0 bit PD0, PD1, PD2 and PD3. We are trying to check this. So if bit 3 PD3 is 0 and I am adding it with 1, if the result is 0, then I do this. Please see this. This is not. It means I take GPIOD IDR and it with 0 0 0 0 1 0 0 0, and if this bit is 1, then the result will be 1 and this will become false, right? On the other hand, if the bit becomes 0, then result will be 0 from here to here. And so if this is true, then only, if this is true, then only it will enter into B equal to 0 1 0, right? If this is false, it will not. So friends, let us go and take a look at the program. I don't want USART to play any role, so I comment this so that it will not go to generate interrupt. But PD will definitely generate interrupt. So I build the program. Yes to all. Let us see what happens at the bottom. Yeah. This time it has taken quite some time. Yeah. Very good. And it has completed this. No errors, no warnings. And so we can now transfer the program into the device to start debugging. So let us transfer the code so generated. Okay, swim ST-Link is connected, so okay. It is building. Yes, 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 done. Yes. Now I will reset it. So it goes to the starting point, main, the first instruction, that is where it has gone when I reset it. And now let me run. Let me run. It will not stop anywhere because I have not pressed the key. which key I'm going to press? I'll show you a picture. This is the key I'm going to press. Okay. Let me go back to the program. And when interrupt happens, what happens when interrupt happens? Something will happen and it will be reflected in these registers. So let me press the key. Here I go. See what has happened? It has entered the interrupt handle, external interrupt port D handler, and it has done all this. And because the key was pressed, therefore this thing was 0. The AND operation gave me a 0 result, and it was negated, therefore 0 has become 1, and therefore the content from here to here is logic 1, and therefore it goes inside this and sets b is equal to 1 0. So b is equal to 0x10. It means it has come here. Once again I run. You can see I am going to run it now, but before that let me move a step forward so that you will see that it is coming back. Now I run it. I am not pressing any key, so nothing stops. It keeps doing its main program activity. It will keep doing whatever is written between while one braces. It will keep doing this. Now I am pressing the key. So it has interrupted the main program. Normally this breakpoint will not be there. It will do this and then reverse back to from where it has come, right? So friends, this is how the port D interrupt has been used. This program does not carry any meaning beyond telling us that an interrupt has been handled. That's it. Making b equal to 1 0 has no other useful value for our project, but for understanding this is of use. Then I activate the other part, which is comms, the communication part. Here I had disabled. Now I will enable this. I cannot do that here. I will have to stop debugging. As you can see, I stopped debugging, and now I can remove the comments. Now I'm sending something on transmit pin. I'm sending 01000001 on the transmit pin, and I'm shorting the transmit pin. I'm shorting the transmit pin here. What I'm going to send is, I'm going to send that 0x41 along this, but I'm not sending it to this device. I say come back and enter the RX pin. This is what I have done. I shorted these two pins together. So whatever comes from out of pin 2 will enter pin 3. So there will be a receive interrupt. This is how we are generating receive interrupt. We have seen it before also. Without interrupts also, we have seen how data moves in serial ports. So this is how it is. Coming back. Now I am sending 41 on transmit, and only once. I am not sending it again and again. And therefore we expect an interrupt to occur just once. And then what will happen? Let us see. What will happen? It is here. When interrupt occurs on serial port, it checks whether it is a serial interrupt, confirms that yes, it is a serial interrupt, and then you write usart1 underscore SR. What does it mean? It means that it will empty this register SR. This is the status register. Because if I don't empty the status register, then it will continue to see the interrupt flag, and although interrupt has come only once, but because the flag is set, Therefore, it always thinks that there is an interrupt and will keep running inside this all the time. So interrupt flag has to be clear. For that purpose, you write usart1 underscore sr. You can also write it in a slightly different way, which is you initialize it to some value like a equal to usart1 sr. We can do that also. But now what we have done is, after emptying the SR, that is the interrupt flags, we have read the value of usart1 dr. That is, whatever we have received on serial port has been transferred to a variable called a, and therefore you will see a to receive 0x41, right? Because we have sent 0x41, and because it is receiving it, so it will see 0x41. Shall we see? Now, let us build it again. Why to build again? Because I have just now removed the comments from here. So the program has changed, and therefore we need to rebuild it. Rebuild all. Yes to all. Every time you need not do yes to all, you can just do yes to whatever the first one. But I have made it a habit. It's better. So what happens? Yes, 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 yes. Zero errors and zero warning. So it has been built without any error. Now I want to transfer this revised program into my device. You know what is our device? This is our device. I had pressed this key just now. Okay. So coming back, and I transfer it to that device. The program is being transferred. I have assured that yes, swim has been connected. So it is transferring, it has gone here. Now let me reset it. When I reset it, program control will come to the line next to main. The first instruction in main function will be executed. So I reset it, and you will see the pointer has come here at line number 19. So this is for resetting, restart application. So it has come here. That is what we expected, and we can see that a has to become 0x41. A is here. It is right now 0, 0. So this 0, 0 will come there. So I say run, run. It has stopped at this breakpoint. And has A become 41? Yes, it has become 41. Will it interrupt again? No, because I am not sending 41 again and again. I have sent it just once. Here, I sent it just once. It is not under a repetitive operation. The repetitive operation has started from here. These instructions from 19 to 25 will be executed only once, and instructions in while one loop will be executed in an infinite loop. That is, whatever is written from this line number 28 to line number 42 will be executed in an infinite loop, right? So now if I ask it to run again, it will not stop at the breakpoint. Let us see. It is not stopping. It just doesn't stop. I allowed the key interrupt to be active, and therefore if I press the key, let us see what happens. See, when I press the key, then interrupt occurred. Which interrupt occurred? External interrupt port D has occurred, and therefore B has become 0x10, right? So friends, this is what I wanted to communicate with you. These are the two kinds of interrupts that we are going to handle, and maybe if as the product evolves, if necessary, we can even incorporate another interrupt. So we will come to that as our product grows. And now where we are going? Let us see where we have to go. Where we go? We are done step 1, step 2, and we are in step 3. In this we have handled IO ports, we have handled serial ports, we have handled just now interrupts. And so in the next lecture we will have a look at MP3 device, the module which is going to help us make the files talk. There will be files in the memory chip, and those files will start talking with the MP3 device. So we will take a closer look at MP3 device in the next lecture. Thank you, friends. If you have any difficulty, you can contact me, or you may revisit these lectures until you are satisfied. So until then, thank you.